So, the next question is, what is the real purpose of a holdout, and what really is a fold? So, the purpose of our holdout is so that we can have a final score or measure to report on how good is what we did. It's something where we didn't look at it, we had absolutely no knowledge about what's in there. It's something that our algorithm had no way of learning anything about, and knowing how well it does on that should generalize pretty well to other things that it has literally no information about. So it should be just like what you have in the real world, where I'm throwing in something the algorithm wasn't able to tune or train or practice or learn about. It's just, oh hey, here's something brand new. How am I going to do on it? That's what a holdout is for that final reporting. As for what a fold is, that's when we had, instead of going train, test, holdout, and we have rows 1, 2, 3, 4, 60, 61, 80, 81, 100. So 60 rows of data training, 20 rows of testing, 20 rows of holdout. This is the pretty typical validation, the train test holdout. And this is going to be, we teach our model on this. Our model says, okay, how well did I do on this? Okay, that's worth noting. I'll write that down somewhere. Let's try doing something different. How well does it do on this? Okay, cool, I'll write that down. Repeat a bunch of times. Okay, I've got a bunch of things written down. Which of them is cool? Okay, let's try something else that's more like that. I'll build some new models. This training data, look down here, how is it compared to the one that used to be awesome? And then once you're done with all of those, then you go final report. Build something on all of these using, I learned how to make it good up here. Let's run it on this, and run it on. All of this is training, and figure out how well it does.
Okay.
So that is what a typical train test holdout split is. Folds come from n-fold cross-validation. So instead of saying we'll use the same training each time, with saying let's try this, see how well it did, we're going to, let's see, we'll call it threefold cross-validation. And I will go train test and test train and train test. So I'm still not touching the holdout until the very end. The holdout still only is going to show up once I'm ready for that final score. But instead of saying, let's build it on this and see how well it does on this, I'm going to build it 3 times. Once on this and check how good it is against here. Once on this, see how good it is against here. And once on this to see how good it is against here. I'm then going to get 3 scores out of it. So we got a 0.7, a 0.8, and a 0.77. That will let me say that on average, this one is, I don't know, 0.76 or so. By taking the average of these 3, which would be just like doing it on one split over here, but with a couple big advantages. One, if this test data has something really weird about it, or if this train data has something really weird about it, if I'm only running on this train test split, I'll never find out that it screwed up because some of the rows were weird.
makes sense.
With cross-validation, everything is trained data a bunch of times, and everything is test data once. So if something is weird, we'll know about it and we'll be trying it. So there's no way that a really screwed up row is going to get missed. The second advantage we get from it is that we can find out how stable it is. So this right here, these two are pretty close to each other. This is less close. So let's say instead this is like horrible, 0.4 over here. Our average could still be above our, that's good enough, or it's better than what we had. But the fact that we have two that are really close, or a bunch that are really close together, and one crazy nonsense over here, that means that this is an algorithm that is highly dependent on what data is fed into it. And if it changes a lot based on what is fed into it, that is a big red flag. Because it suddenly means that maybe some of your data is bad, maybe it can't handle a certain situation very well, but that certain situation only happened when you combined these two folds. Because like over here, oh, it didn't take up enough to hurt it. Over here, it didn't take up enough to hurt it. But when it's just looking at those, suddenly it's all fire and brimstone. So being able to see, man, there's a lot of variance here, this is an unstable algorithm, can also be a red flag even beyond just looking at your average score. As for what specifically a fold is, I'm splitting it into 3 folds, and each fold is a chunk that will be in testing once and then be trained the rest. So there's 3 folds, so a third of the data is one of the folds. The first fold is the one that is test in fold 1. The second fold is the one that is test in fold 2.
Okay.
And that's all independent of holdout. Although because you are taking an average and stability, oftentimes you can get away with reporting, oh, this is the result of 5-fold cross-validation. And that's good enough, it's what a lot of scientific research does. But it's still good practice to have holdout.